So we're going to be starting to talk about a little bit more complex ways to take derivatives of functions. In the previous chapter, we looked at some pretty basic derivative rules, sort of laid the groundwork, and then in this chapter, we're going to look at how do you take derivatives of things that are not so straightforward. We're going to start today with something called implicit differentiation. So let's review what we kind of already know. If I said in the directions, find dy dx for the following function, the first thing you would do for this particular problem is you would have to get y by itself. This means find the derivative of y. So we would need y to be by itself. If we rearrange this, we get negative 3x squared plus 2x minus 7. Then when I take the derivative, I would just use the power rule and I would get negative 6x plus 2 is my final answer. Sometimes, however, it's not quite so easy to get y by itself. For example, if we look at this problem, getting y by itself because there's a squared would be a real challenge. If we look at problem 2 here, getting y by itself because it's inside of a tangent function would again be a real challenge. So what we need to learn is how do we get y by itself? How do we get the derivative without having to get y by itself? We use something called implicit differentiation, which comes from this word implicit notation. Implicit notation means that a function is not written with y by itself. For example, tangent of xy equals 1. The y is not by itself. Now, when we do implicit differentiation, the nice thing about this process is that it doesn't require the y to be by itself when we take the derivative. So it saves us the work of trying to figure out how would you even do that for this problem. Sometimes it is much easier to take the derivative of a function that is defined implicitly if we don't have to solve for y first. In these types of problems, we know that y really represents an entire function. If we could get y by itself, it would be equal to all of this stuff. So when we take these derivatives, we will need to treat the derivative of y a little differently than we treat the derivative of x. What this means is that every time you take the derivative of a y, you will need to apply the chain rule. And what the chain rule says is that you have to take the derivative of what y represents. To represent that we are doing that without doing it definitively, we would write dy over dx every time we take the derivative. Now this sounds harder than it really is. I think it'll make a lot more sense once you actually see it in action, so just go with me here for a second. First, we would differentiate both sides of the equation with respect to x. Collect all of the terms that have a dy over dx in them on one side of the equation. So you're going to have to do some rearranging. Factor out the dy over dx on that side of the equation, and then solve for dy over dx. In the end, dy over dx needs to be isolated to be alone at the end of the problem. That's your goal. At the very end, we should still have dy over dx equals some stuff. Only in these types of problems, dy over dx might equal some stuff, and the stuff might have a y in it. It might be part of the answer. You can tell that we need to use this technique because the function will be defined implicitly. The y will not be by itself. So let's see this in action. What does this actually look like? If I look at this first example, it says use implicit differentiation to find dy dx. So I'm even telling you in the directions, you got to follow a slightly different process here by saying implicit differentiation. Even if I didn't say that, you would know that that was necessary because the y is not by itself. So let's take the derivative. The derivative of x squared would just be 2x plus the derivative of y squared, here's the new thing, I'm doing it in a new color, would be 2y, and then since we're taking the derivative of a y, we would write times dy dx equals The derivative of 25 is 0. This is one mistake I see a lot, is that students will still keep the 25 there. I like to joke that you get so excited about finding the derivative of the y that you forget to take the derivative of the number, but a derivative of a number is always just 0. Now our goal here at the next part is to get the dy dx by itself. So think about this as just sort of solving an equation. First, we would subtract the 2x on both sides, which means we would have 2y times dy over dx equals negative 2x. Then we would divide by 2y on both sides. So we would get dy over dx equals negative 2x divided by 2y. And then your last thing that you're going to want to do is simplify that. Believe me, this is going to pay off knowing to simplify. And you would just cancel the 2's because they're both divisible by 2. So you would get negative x over y, and that's your answer. Now this is what I would call like the most basic, straightforward example possible. So let's try problem 2. Problem 2 says x plus tangent of x times y equals 0. You can tell already because of the way the problem is written, it's going to be a little bit more complicated. So let's take the derivative. The derivative of x is 1 plus the derivative of tangent would be secant squared, and we leave the inside alone. But since the inside has a product in it, we need to use the product rule here. So, product rule says, copy the x, take the derivative of y. Now the derivative of y would just be 1, but because it's a y, we need to multiply by dy over dx. Plus, copy the y, take the derivative of x would just be 1, equals the derivative of 0 is just 0. Now remember, our goal here is to get the dy over dx by itself. So let's do some solving. I would start by subtracting the 1 on both sides. So I would get secant squared of xy, parentheses, x times dy over dx plus y equals negative 1. Now again, I'm trying to get this by itself. So I'm going to divide by the secant squared of xy. So I would have x times dy over dx plus y equals negative 1 over secant squared of xy. Then I would subtract y. So I would get x times dy over dx equals 1 over secant is you can't really see. 1 over secant is really cosine, so we would have negative cosine squared of xy minus y, and then we would divide by x, so dy over dx equals negative cosine squared of xy minus y all over x. And we're done. Now, if you think about this problem in the big picture, the only calculus thing that we did here was the first step. After that, it was all algebraing, which is where the real challenge is going to be. So we're going to have to practice this a lot because there are lots of little places to make a mistake. Let's try number 3. We're going to take the derivative. So we're going to have 10y, and then don't forget to put the dy over dx. Plus, the derivative sign would be cosine of y, and then don't forget to put dy dx. Equals the derivative of x squared would be 2x. Now you'll notice this problem is a little bit different because there are two different terms here that both have a dy dx. So in order to solve for it, I'm going to need to factor it out. So I'm going to factor it out, and I get 10y plus cosine of y left on the inside of the parentheses. And then lastly, I would just divide. So dy over dx equals 2x divided by 10y plus cosine of y. And you're done. Now we saved the best for last. So this one is going to be pretty complicated, and here's why. Take a very close look at the problem. Do you notice that there's a product here and a product here? So we're going to have to do product rule twice. The first product rule, and I'm going to do this in two different colors, would be copy the x squared derivative of y, so dy over dx, plus copy the y, derivative of x squared is 2x. Now my second product rule would be copy the x, derivative of y would be 2y times dy dx, plus copy the y squared, derivative of x is just 1, so equals 0 because the derivative of 6 is 0. Now you'll notice I have several terms here that have a dy dx in them. This one and this one. So the first thing I'm going to do is keep these things on this side and move the other two terms to the other side. So I'm going to subtract. I'm going to have x squared dy dx. I'm going to leave that here. Plus, and now I'm just going to make this part look a little bit prettier, 2xy dy dx equals subtract 2xy, subtract y squared. So again, I'm subtracting this, and that's how I get this. Now, both of these terms have a dy dx in them. So to get that by itself, I'm going to need to factor it out. And what's left would be x squared plus 2xy equals negative 2xy minus y squared. So my final answer would be dy over dx equals negative 2xy minus y squared over x squared plus 2xy. And we're done. Okay, that's it for the first day. Getting started, and yeah, we're done.